And welcome back to another lecture for solar energy conversion systems, dealing with time and space relationships and how we all tie that together with our ideas of irradiance, the intensity of the light that's incident upon Earth and upon our solar collectors that we're working with. And a lot of this is tied into the goal of solar design. So we're reading from Chapter 6 of Solar Energy Conversion Systems, where we really set up the idea that the Earth and the atmosphere are interacting as just, we've learned so far that they're interacting as one big solar energy conversion system. But we're thinking about our solar energy conversion systems like photovoltaics and solar hot water systems and even buildings on the ground in a given place, right? The goal of solar design is to maximize solar utility for your clients or stakeholders in a given locale, to seek out that highest preference for solar goods and services in a given locale on behalf of that client that you're talking about. The three really kind of fundamental ways that we can dig into that in the tools that we're learning right now are going to be tied to angular relationships and shadows. So we can reduce the cosine projection effect by basically tilting our collectors to face the general direction that the sun will trend across the entire year. We can also reduce the angle of incidence between the beam of the sun and our aperture or receiver in our solar energy conversion system by tracking the device in some way, tracking the sun in some way. And if we are looking to gain that solar energy, to get a solar gain, we would try to reduce losses from shadowing. And shadowing is going to be a big deal in the coming reading material in Chapter 7. And so we really want to get a lock on why we're doing these calculations. We've introduced in the past two lectures the ideas that everything that we're doing is going to be done in terms of angular relations, that we're going to calculate almost everything in terms of angles, and it's all related by what we call spherical trigonometry. Fundamentally, the way that Google Earth works, the way that our GIS systems work, the way that our satellites work, the way that time and space on Earth are united. So let's move forward and tie that to our understanding of the intensity of the sun, right? So we know that if we are in one of the extremes of the hemisphere, say we're past the tropics, we know that time and place and solar intensity really are linked together. If we're in the quote-unquote summertime, we have a lot more solar irradiance hitting the Earth. And why is that? It's because the Earth is being tilted towards the sun. The declination is such that the Earth is tilting towards the sun, and either the northern or the southern hemispheres are getting more irradiance than they would have gotten if they were tilting away from the sun in their daily rotations. Right? And when you're tilting toward or away from the sun, you're experiencing more or less of the cosine projection effect. That is where the same amount of photons are spread out over a wider area, just like tilting a flashlight at a low angle across a table. It'll send the same amount of photons across a bigger area. Now, if you live in that small part of that area, you see less photons hitting your solar energy conversion device. We are all going to connect this starting with something that we've introduced in class called air mass zero. And that's going to be the intensity of the sun's light just outside of the atmosphere of the Earth. Now, to get that, we start with the idea of what is the average annual air mass zero. And that's something that is actually research. That's an empirical measurement that was recently updated by NASA through satellite measurements, and that average annual air mass zero is called the GSC. Remember, G is our symbol for total irradiance or global irradiance, and SC is the solar constant. We're just going to call GSC the solar constant, and the solar constant has been found to be 1,361 watts per square meter. Yes, there's variability in that. It's an average, but that's the unit that we're going to use as our starting point. That's going to be equal to, in another notation, G bar, or the average of the irradiance just outside of the atmosphere, that's the subscript 0, of the normal to the sun. That is the normal to the surface of the sun. So N is the beam directly normal to the irradiance of the surface of the sun. So DNI, or that's the average measurement right there. The intensity collected on the plane perpendicular to the normal radiance is GON with no atmosphere, so bar is the average. There we go. All right. Now, that's great, but how do we calculate the day of, like any day, of the normal irradiance just outside of the atmosphere? We're not even going to worry about how the sky and the clouds will change things. We're just going to calculate what's supposed to hit just outside of the Earth's atmosphere based on that average value. And so we know that this varies with seasons and tilt of the Earth, and everything that we're talking about here now is going to be done in solar time only. So we will only deal with solar time from here on out. All of our time corrections were to get us into solar time. We're now in solar time. So if I want to get my daily normal irradiance, I'm going to have a modifier of my solar constant, the average. And so I'm going to need to know what's the day of the year, and you're going to see that function of the cosine of 360 degrees times n day divided by 365 days. All of our years right now are average years of 365 days only. And I'm going to get a G naught n, or a normal irradiance on the surface of the Earth, based off of the solar constant. So it's just a cosine function that is modifying that 1,361 watts per square meter. Okay? And this is just rate the normal irradiance. This doesn't tell us about any horizontal surface on the Earth. We're going to need to do a modification to get what the irradiance on just a horizontal surface of the Earth is. So GON is the beam normal to the Earth. That could be any angle of incidence. We're going to need to correct that. So air mass 0 on any horizontal surface, we're still going to be assuming that we didn't have atmospheric effects, is going to be a corrected equation, which is 6.18, and it's just G naught. So you've seen us go from GS, the solar constant, to G bar ON, to GON, well, that was G bar ON, to GON, the normal irradiance, to GO, or G naught. That value, now I have GON for that specific day, which I calculated from my average value using, let me just go back, using equation 6.17. You see that I'm using the solar constant to get GON, or G naught N, but I'm looking for the horizontal version of that in 6.18. So we've got a couple of steps that we've built in here. Now, in order to get that correction, I need to know the latitude of the site that I'm interested in on the planet of the Earth, because the latitude will affect, how far north or far south away from the equator will affect the cosine projection effect, which will affect how we change the value from GON. And the declination will also have a factor in that, because the declination tells us how far we've deviated throughout the course of the year from plus or minus 23.45 degrees. The next portion of that equation is a string of cosine functions on the latitude, the declination, which I just explained. We need to know where we are on the planet, north or south, what day of the year it is, which effectively we're getting through the declination number, and now the hour angle, which is telling me what time of the day it is, and the time of the day will also affect the cosine projection effect on a horizontal surface. All of these come together to give you G naught, which will be still in units of watts per square meter. And that will be the instantaneous irradiance, the incident solar shortwave global energy for air mass 0, just outer space, on a horizontal surface. The interesting thing here is if we look at our textbook reading, we find out that this red chunk that we have is actually equivalent to the sine of alpha S. That's equation 6.26 on page 165 of Solar Energy Conversion Systems. So it's good to know that these things are all being lumped together. As the equations get longer and longer, we actually find out that many of them are just representative chunks of different key coordinates in our spherical trigonometry system. G naught then is going to be G naught n, or G0n or GON, times the sine of the altitude angle of the sun, right? So however high the sun is in the sky will affect the cosine projection effect on a given day. If we wanted to solve for that, we'd need G solar constant to solve for G naught n, and then we need to calculate for the sine of the altitude angle. Now, thinking about this, I want you to remember that even though we're going through these materials fairly fast, because we are in video form, feel free to pause, to go back, to check the textbook, and to do some comparative reading back and forth. So when we talk about energy density here, this is pretty important. If I were to integrate any one of these data into, say, an order of hours or so, we would be going up into joules per meter squared from watts. If I'm talking about megajoules per meter squared, which is oftentimes a more useful unit for the quantity of energy that actually is incident upon our Earth and the solar panels that we're dealing with, you're going to need to multiply any joules per mole unit times 10 to the 6th. And that's going to come into play in a couple of future equations. So, 6.19. If I need an hour of data, I'm going to integrate across an hour of irradiance. If I integrate it across time, then irradiance would become irradiation, T-I-O-N, because I have hourly irradiation. Now, as a coincidence, hourly irradiation is given the symbol I. So we go from G to I. It still means the net irradiation coming in on a horizontal surface. The not symbol, or the 0 or the O in the subscript, means it's not considering an atmosphere, just outside the atmosphere, or like Earth without an atmosphere. And then we have 12 times 3,600 divided by pi times the G naught n. And so we've got a conversion in here of 12 hours in a half of a day, 3,600 seconds in an hour being represented here, and then G naught. And so we're going to have a few conversions in here, and I'm writing down these equations to show this, that the pi over 180 is therefore a conversion of units, and I'm going to have differences in hour angles. So I'm going to have from the final hour angle minus the initial hour angle in the front of that sine phi sine delta portion of the equation, which is right up there in 618 as well. We're just adding a block of time into that equation, and we add that block of time into the cosine portion of the equation by not having the cosine of omega as you're seeing in equation 6.18, but instead we include the sine of the final hour minus the sine of the initial hour. And that angular difference is going to give us the irradiation. It will give it to us in joules, and so we'll need to factor that in terms of converting that value, which will be a very large number, into a more reasonable printed number in terms of megajoules. Okay, so take the energy density as irradiation, and let's think about it in terms of an entire day. We've done 1 hour. Now let's do this in terms of an entire day. Now, again, the equation is written simply to deliver units of joules per meter squared. We're going to need a unit conversion to get it into megajoules. So here, a daily irradiation in our solar textbook and in standard notation for journals for solar energy is H. So we go from G to I to H. H is the daily irradiation. You're seeing a lot of similar factors right in red before that. I'm going to have a number 2 because I'm multiplying 2 hemispheres of the day, 2 half days together, and I'm going to need to find out what the hour angle of the sunset is. That is omega SS of the sunset angle. And we're using the sunset angle specifically because we remember that the time in hour angles is positive in the afternoon. And we'd rather just put in a positive value in there rather than negative values. So in order to find the sunset angle, and this really gets tied to also the length of the day, because if I can find the sunset angle in terms of degrees, I could double that, and I would then have, in terms of degrees, the length of my day. So the sunset angle is the arc cosine, or A cosine D in our Scilab or MATLAB or Python coding, of negative tangent phi, the latitude, tangent delta, the declination. That's really sine over cosine, so we're seeing that same representation of sine, latitude, sine, declination over cosine, latitude, cosine, declination represented here. And that's going to give us a sunset hour, which will be a positive value. And it's going to be a positive value because in my basis for hour angles, the solar noon is an hour angle of 0. Anything to the afternoon is adding time. Anything to the morning is subtracting time. So my day length becomes 2 times the sunset angle. And this is again what I was trying to demonstrate. That solar noon is an hour angle of 0. If I go in towards the afternoon, I have a positive value. If I go towards the negative, I have or sunrise, I have a negative value. And here in equation 6.25, we're just keeping things relatively direct by gathering 2 times the length of the day, that's what you're seeing in terms of day length, as 2 times the sunset angle. All right? Now, there's an interesting factor here that was found out through research. A lot of good research in solar energy. And some great research emerged from the University of Wisconsin-Madison. What was found out, and what we've been knowing for some time from meteorologists as well, is that days inside of each month are really statistically similar to each other. And particularly when we take out the atmospheric effects. So days of the month in terms of air mass 0 are truly statistically similar. So what came about was a Professor Klein at the University of Wisconsin, when he was early in his research years, was working with the team and found that you could describe the average day of air mass 0 in a way that didn't require you to, say, measure or calculate air mass 0 for 28 to 31 days and then divide it out and then get an average. You could actually find that one of those days in the month would have a value of daily irradiation that would be very, very close enough for us in design to be equivalent to the average of the value. And so came about the average day, the average energy day, in fact, for each month of air mass 0. So this is on page 163, table 6.3. You've got a list of average energy days. And notice here that we've got average energy days in January. That would be January 17th. So every year, regardless of the weather, because we are dealing with air mass 0, January 17th will be representative of the average irradiation of all 31 days. Similarly, February 16th, March 16th, April 15th, and so on. You select a single day that matches or is close enough, significantly close enough to the monthly mean, and you do that for calculation, and it really reduces the number of calculations that you need to do. But it also reveals something really interesting about the sun and declination. Now, you might have remembered from one of the earlier lectures that I talked about how the declination change is actually very small about the solstice. In fact, it hangs around less than 6 degrees for about 80 days. So the average day that you see around the summer solstice and the average day that you see around the winter solstice is actually very far from the midpoint, which you would expect to be around the 15th. So June is not on the 15th of June. June is on the 11th of June because the declination change is slow. And about June and July, we start getting closer to that value. But December and January are, so we see June and July have days that are diverging, but mainly December to January has that same kind of shift from day 10 to day 17. And as we get closer and closer to the equinox, those months seem to have their average energy days right about the middle of the month. Okay? Great little kind of insight just looking at the way that the average days are laid out, that tells us about that rate of change of the declination and the length of days over the course of these years, over the year, excuse me. All right? So it's an unusual term, the average energy day, and it takes a little getting used to, but I really find it to be a very valuable tool in making calculations for solar energy design. Okay, so let's change the perspective. Let's bring things right back down to Earth, down to the sun in relationship to an observer on the ground. That could be a person, that could be a panel. We're on the ground. We need to know about sun observer angles. And we basically built everything up to this point to tie together that air mass zero irradiation with any of the other angular corrections, because the sun, what we've corrected for up until now is a panel or a solar energy conversion system that is lying horizontally. But I've just said in the beginning of this lecture that the goal of solar energy design would be tied into minimizing the angle of incidence and reducing that cosine projection effect. So let's think about this. We're going to think about this in terms of new angular relationships that we haven't really addressed. We've kind of introduced a couple lectures back, but they're specific to the observer on the ground. Okay? All right. So, okay, so there's no collector yet, but I will be introducing a collector. If I look at this figure, I'm going to see that I have the sun that is elevated into the sky through the solar altitude. The solar altitude angle is between the critical point, which is pointing at the sun, and the horizontal plane on the ground. Let's assume for the moment that we're on the Great Plains and we don't have mountains or hills around us. We just have a flat horizontal plane in front of us. The angle from horizontal up to the sun is going to be the solar altitude angle. And that's still an alpha angle, an altitude angle. In general, an altitude angle is alpha, but we're raising that altitude angle up to the critical point that is the sun. The complement of that angle is going from the zenith. If you look at that plot, there's a Z in the going up and down. That's the zenith. The zenith angle is the complement of that, and that would be the angle of incidence relative to a flat surface, right? So, what's left? Well, what's left is the other independent coordinate, which is the rotational angle. The solar azimuth is the rotation across the horizontal surface. So you're rotating or spinning around without any up or down movement. And in this case, the azimuthal angle is the azimuth of the sun, and it's the projection of the sun down onto the horizontal and then rotating across. And in this case, we've got between the critical point of the sun and the origin point at 0 degrees. And quite often we use the origin point in our calculations to be pointing towards the equator. So in northern hemisphere, that would be 0 would be south. There are conventions that we mention in the textbook where 0 is north and we go 360 degrees clockwise as meteorologists use. But for the purposes of solving these math problems, it's actually a lot easier to stick with a similar convention of solar noon, which is 0 degrees pointing south in the northern hemisphere, and negative towards the morning when I'm subtracting time, and positive rotation towards the afternoon. Alright, so more on the sun observer angles. If I want to get the equations for those, you'll see that I come back to equation 6.26, which was fundamental to my G normal atmosphere at air mass 0. That was the sine of alpha S. That's equation 6.26. Equation 6.27 is the complement of that. A lot of similarities going on there. Because the cosine of 1 is equal to the sine of the complement. So it's the same equation that we're seeing here. One more time. The sine of alpha S is equal to the cosine of theta z. This was in one of our earlier lectures, which is why both equations have the same red section in between. A reminder here, the latitude, phi, is going to represent my place on the planet, north or south. The declination, delta, is going to represent the day of the year. And then the cosine of the hour angle, omega, is going to tell me the instant in time. So I've got place and time all coupled together in one equation. Now, if I look at 6.28, I have the equation for the azimuth angle. And the azimuth angle has a weird little convention here, sine, and that has nothing to do with trigonometry. It is positive and negative. It is basically an on-off signal. If the hour angle is greater than 0, then you make the sine positive. If the hour angle is less than 0, then you make a negative sign in front of that absolute value. All right? So don't get too confused, but this is the sine convention is basically just saying it's positive if the hour angle is greater than 0, negative if the hour angle is less than 0, which is basically a case-based way of representing the equation. Then I'm going to have the arc cosine of some of the zenith angles, the latitude, and the declination. Okay, so now I'm going to get to talk about these two types of gamma S, which is if I choose to do my azimuth using the equator as 0, then east will be, true east will be negative 90 degrees, true due west would be positive 90 degrees. Traditionally, this is the way we would do it in solar, and it's very easy to learn and connect together the math of what's going on. So this is what we teach, and this is what we'll work with for the majority of this section of learning. However, it's very important to know about the other type because it's what meteorologists use, and it's where north is 0 degrees, east, and then it goes around a full 360 degrees rotation. East becomes 90 degrees, south is 180, and west is 270 degrees. You will see in System Advisor Model, SAM, that both of these conventions are explained specifically as to which one is being used in the tool. It's what makes SAM a really useful educational tool as well. It specifies which of the algorithms are being used and what the convention is. So just keep an eye on that because the azimuth angle does have two conventions. We will teach based off of the equator. Pointing towards the equator is 0, which then makes it the same way north or south. And in the type 2 for meteorologists, north is always 0, independent of whether you are in the northern hemisphere or the southern hemisphere. Okay? All right. So, coming up next will be this idea of collector sun angles with shading and tilting things and the orientation of all of our panels. And so we're going to be talking about critical angles for other objects than just the sun. So far, alpha S was the altitude angle up to the critical point of the sun. In the future, we're going to have other critical points that would be shading devices, like other buildings that might block our images. We're also going to bring back from our original initial lecture on these time and space relationships the general angles of the tilt, beta, of my collector, and the azimuth, gamma, of my collector. Now, very important things here. Beta and gamma, when they are tied to the angle of incidence for my collector, that is beta and gamma of my collector. That gamma is not the azimuth angle of the sun. And a lot of people can get the problems wrong when they're doing calculations by entering that in. So if beta is red and gamma is blue, and we're going to look at this rather long equation 630. 630 is the equation for the cosine of the angle of incidence. And so we'd have to solve for the arc cosine to get the angle of incidence in any one case. Now let's look at that. Beta pops up in many of these different spaces, and it's tied in to still that sine phi sine delta and cosine delta sine delta. So all of those angular relationships are tied in much like you've seen before in other relationships. And this is where the gammas come in. And the gammas, again, are the angles of azimuth of my solar panel. So if I had a photovoltaic panel, and I were to do as we're learning now, and not to face the panel due south, but actually to collect some of the afternoon sun. And so I would rotate my panel to point it more towards the southwest. I would give it a gamma of, say, plus 10 degrees because I rotated along a horizontal plane. I rotated about 10 degrees into the afternoon, plus 10. Then I'd have cosine of 10 degrees in all of these arguments. Let's say my collector tilt was tilted up 30 degrees. That would be the cosine of 30 degrees in all of these arguments. Keep in mind that all of these equations are written for degree-based arguments, so you will need to use your calculators in terms of degree-based arguments, in terms of a lot of the solutions that we're using. Okay. Other things is that we're heading towards plotting our solar critical points onto what's called sun charts. And sun charts themselves are broken up into polar charts, where the projection of the entire solar dome is flattened onto a circle, or ortho projections, where that solar dome is projected outward onto a horizontal surface that you're seeing here in this sun chart from the University of Oregon's Solar Radiation Monitoring Laboratory. In this case of the orthogonal plots, which you're going to be working with, gamma is essentially your x-axis, and alpha becomes then your y-axis. So gamma S and alpha S of these blue lines that you're seeing here are actually the plots of the arc of the sun going through the day for 1/2 of the year, with solar time being considered. More on that later, but thanks so much for your time today, and I look forward to talking to you in our next lecture.